Nice one. There's always issues. Um, well, thank you very much, Karen, for the introduction. My name's Domhnall Finch. Currently working with the National Parks and Wildlife Service. But I'll just give, I suppose, a brief presentation on some of my work relating to bats. I did my PhD on greater horseshoe bats over in England a couple of years ago. So the majority of what I'll probably talk about is in relation to some of my chapters associated with the PhD, and then some of the work we have done in Ireland since then. So we're looking at modeling functional connectivity of bat species, and essentially then how to use these kind of computer models and graphics to aid strategic planning. I suppose if you're looking at houses or anything like that in terms of development, and then species, how to target species conservation. So when we're looking at a landscape, what are we actually looking at? When we break it down from a species perspective, we're really looking at compositions and configuration. So composition would be the proportion of each habitat within an area. So for example, this image here from the plane, you might calculate how much grassland is out there, how much woodland, but it doesn't give any specifics in terms of how they're spatially arranged. And so configuration then comes in on the other side and looks how they're spatially arranged. For example, if a woodland is close to each other, it might provide more habitat for certain species versus if it's more fragmented, you may not get woodland specialist or something like that. So each of configuration and composition of a landscape can really influence how species are present within the landscape, and then also then how they move within the landscape. And then when we're trying to break down sort of within configuration, you're looking at connectivity within that. There's two different elements to connectivity. There's physical connectivity, and that would be, say, for example, this image, that would be the tree lines either side the road. Each tree line is connected to itself. However, there's a gap between the two of them, so they're not physically connected. And that can actually have a huge impact on species movement or incur costs for species. And how we kind of look to measure that cost will be looking then at functional connectivity. And that is each habitat will kind of have different value to it, how permeable it is to species movement across the landscape. So if, for example, the species moving from the left-hand tree line to the right-hand tree line, what cost is incurred by that species moving across the landscape? So it might be an energetic cost, or it might be an increased risk of predation. So those are the kind of examples of how what might act as a barrier for species movement in the landscape and the costs that occur to that species. So over kind of the next couple of slides, I'm going to go through some of my chapters and kind of examine how different features, so we ran experiments, just how different features within the landscape associate with bats in terms of their activity and how that relates to then functional connectivity within the landscape for bats. As I kind of said, the majority of this work is done over in England, and my study species was the greater horseshoe bat. It translates very well for the lesser horseshoe bat in Ireland in terms of the ecology. The greater horseshoe bat and lesser horseshoe bat are very similar in ecology. So kind of the results we pick up here are not too different from what we would expect from lesser horseshoes. But one of the first experiments that I looked at was looking at the impact of placing bat detectors in the middle of agricultural fields versus along the linear features surrounding them. And what we found was, as we might expect with bats, we're kind of fully aware that bats like linear features. So we found that 80% of total activity occurred along linear features. This is quite a large proportion of bat activity. However, when we look at noctual species would be very similar to our lizard species. It's roughly 50% of bat passes recorded in the middle of fields versus along linear features. Now, we're also fully aware that, say, lizards or noctuals in this case, their bat passes can be detected much further away. So maybe a bit of bias in that as well. Common and soprano pipistrelle weren't too different in terms of having more bat activity along linear features. And the species we were really interested in was greater horseshoe bat. What we found was roughly 30% of bat passes recorded in the middle of fields. Now, this historically, in the literature, is a species that is highly associated with linear features, within 5 to 10 meters maximum of a linear feature. And so obviously these results are kind of telling us something a little bit different, and goes towards kind of when we're looking at a landscape, what should we, in terms of designing an experiment or designing an ecological impact assessment, what should we really be looking at within the landscape? So we're kind of seeing here that it's really important to look at all features within suitable features within the landscape, rather than just those that we perceive to be important to bats. Anecdotally, what we also found with this, although we didn't have enough data to fully test it, was that the majority of greater horseshoe bat passes that we recorded in the middle of fields occurred late summer, early autumn, kind of, August, September time, which kind of hints at moving towards juveniles, perhaps foraging, looking for new foraging areas, trying to determine what's good, what's bad, potentially being pushed out from favourable foraging areas from adults. It's just an interesting anecdote that we kind of perceived from this information, how they might utilise different landscape features at a seasonal level as well, rather than just once a year as such. Another element of this experiment that we undertook was to examine different linear feature types. And this worked out as managed hedgerow would be the top left, unmanaged hedgerows is your bottom one, and the right-hand side, top right, would be tree lines. So these different landscape features, how the different bats utilised them. What we found was noctules and common pipistrelles, similar, I would say, lizards, similar results would probably be found for lizards, is that there was no significant difference in terms of how they utilised the three different linear feature types. These are quite generalist species as well. We found that soprano pipistrelles were more significantly associated with tree lines and unmanaged hedgerows. And with the greater horseshoe bat, we found that they're only significantly associated with tree lines. So it's kind of really identifies how the species might use the landscape. And what's kind of important out of this is how this feeds into how species interact at a landscape scale, and going back to kind of the configuration of that landscape and the functional connectivity of that landscape. So these, as we're kind of the saying goes, these are the veins of the landscape and species corridors of the landscape. So this kind of information really lets us determine how the species will use the landscape, how the different linear feature types, being unmanaged or managed, can increase permeability within the landscape, and so increase areas for foraging. So these are kind of, this little experiment was mainly associated with what bats are utilising, how important they are. Another element is looking at barriers to bats. So we know, say, with greater horseshoe bats and lesser horseshoe bats, that light fixtures are kind of have huge impact in terms of species movement. One area that hasn't really been looked at before was the impact of traffic noise on bat activity. So we designed an experiment where we played traffic noise out of speakers. So we had control locations which just had detectors recording for 5 nights, and we paired this with our treatment location where we had control nights where we had no traffic noise being played for 2 nights, and then 3 nights of traffic noise being played. And this was kind of done to high-end spec in terms of speakers we had to fully replicate motorway noise, both ultrasonically and within the sonic spectrum. And what we found was that there was no significant difference in terms of control locations between the treatment and control nights. So there are control locations where we had no traffic noise throughout the 5 nights. There was no significant difference in bat activity. However, with where we played the traffic noise, we found that there was a significant drop in bat activity. So when we look at just our treatment locations, we break down the 5 nights. You can see here the white nights 1 and 2. There's quite a bit of bat activity, and your average bat pass per night, are range from 200 to 250 kind of. And then if you look at the grey bars, which is our treatment or our noise nights, night 3, 4, and 5, we see approximately 2/3 drop in bat activity. This is a huge drop in bat activity, and what we found then was in subsequent year, we went out and done another experiment where we broke down sonic and ultrasonic spectrum of traffic noise. So for example, for 2 nights we played sonic spectrum versus 2 nights we played ultrasonic spectrum, and we see how the bats reacted to that. And what we found through that part of the experiment was that the ultrasonic spectrum of bat activity, which we might think and what was taught in the literature would have an impact on bats due to their, their echolocation, how they navigate in the landscape. However, what we found was that the ultrasonic spectrum didn't have a significant impact on bat activity in comparison to the sonic or the audible spectrum of traffic noise. And what this is kind of telling us is that traffic noise is kind of more of a disturbance within the environment rather than interfering of how they move across the landscape or how they perceive the landscape. One of the other parts of this experiment, and kind of relates to how species move within the landscape, is how much of a barrier roads can be to bat species. So not only did we have bat detectors at the speakers, we also had bat detectors kind of 20 and 50 meters away from the speakers. And what we found was that there was significantly less bat activity away from the speakers as well. So between 20 and 50 meters away from the speakers, we were still seeing that drop in bat activity. So that's kind of telling us that it's not just an impact at the exact source of the noise, but also that disseminates into the landscape and makes more of the landscape impermeable to the movement of bat species, not just at a single source. So this is really, again, really important information when you're looking at cumulatively how bat species move within the landscape. And then if you're looking at landscape scale assessments in terms of new roads or new developments or anything like that, and how this can influence their movement. So the likes of those 2 studies are the impact of street lights on horseshoe bats. What does this actually mean? So we're kind of aware that there is negative impacts or there's positive impact by tree lines. How can we use this information at a landscape scale? So this is what I will say, the other elements were based off of kind of all species in terms of pipistrelles or noctules or horseshoe bats. This rest of the presentation is kind of mainly just based on greater horseshoe data, which obviously translate into lesser horseshoe data as well. So utilizing kind of the information of how negative streetlights are or roads, we wanted to see how these might act as a barrier to species movement within the landscape. So we use a software called CircuitScape, and this utilized circuit theory and random walk theory. And essentially this is like a resistance board, and is essentially the flow of energy, across that, like electrical current across the resistance board. So if you see here in the image going from 0 to 4, we have a resistance value of 3 going from 0 to 1, 1 to 2, and 2 to 4. Whereas the lower route going from 0 to 1, 1 to 3, and 3 to 4 has a resistance value of 5. So the lower route is less permeable, kind of essentially to the movement of the species than the upper route. However, one of the good things about using software called CircuitScape is that it has the random walk theory element to it. And as we're kind of fully aware, animals kind of do what they like no matter what. Even if we have streetlights there, we know that we'll record, for example, the odd lesser horseshoe passing them or stuff like that. So this part of the software still allows some energy or movement of species along those less or more resistant areas. Sorry, it doesn't just cut them off straight away to a single least cost path. So how do we utilize the knowledge of the impact of streetlights or roads and these sorts of softwares? So what we did was we went out and collected, I think it was 256 bat detector locations across the landscape in Devon. And we placed these along, every single habitat feature within around the roost location. So underneath street lights, along managed hedgerows, unmanaged hedgerows, rivers, woodland edge, in the middle of woodlands, agricultural fields, because not only are we looking for the high value in terms of high activity points to validate our model, we're also looking for those low values to say that, yes, our presumption is correct, that they aren't flying all the time under streetlights. And what this then allows us to do is we are then able to create resistance scores for each of the habitat features. So we had 5 habitat features. So we had lights, we had land cover, we had distance to roads, distance to rivers, and distance to linear features. And so each of those habitat types, 5 habitat types, are given different values based off of how much species activity occurs in relation to each of them. And then what we can do is combine them all together into one multivariate resistance map. So, for example, if we have, this is important, is that combining them into one rather than looking at them individually. So if we have streetlights, it might be a resistance value of 10 out of 10 in terms of, bats aren't, or greater horseshoe bats aren't going to pass by it on the normal. However, if we have no managed hedgerow or tree line beside it, that might be the case. However, if we add in another element within our map, our landscape, of a tree line beside these lights, the value of the area would reduce in terms of how permeable it is. So it's going to become more permeable in the landscape to the bat species. So it might drop down from 10 to a 7. And this is important in terms of mapping how the energy flows within the landscape. And so once we create these resistance maps and give them all a score, we then combine that with our source layer and our ground layer. So our source layer is where the energy is coming from. So if we switch on that light, it's that initial switch, and that's our roost location. And essentially, that sets out the pulse of the energy. And these go to our ground layer, which we had dots for the energy to go to in a circle every 100 meters, and those circles were every 100 meters out from the location of the roost, if that makes sense. So it's equal dispersal of energy out from the roost. So it isn't that we're looking for the most favorable habitat, for example, a river with good tree lines beside it. It's given equal opportunity for the bats to travel to any location within the landscape. So we put these layers into Circuscape software and produce kind of these the map on the right hand. It kind of just looks a little bit like spaghetti on a plate, kind of, and it's going everywhere in the landscape. But I promise you, they mean things. The different lines. So when we zoom, kind of get a larger image here, and again, I'll overlay it with no S map here and the next one. But in this instance here, the blue color is high energy. So these are areas that are more permeable in the landscape to movement of bat species. So you can see that center point there, which is where the roost is obviously has the highest energy. And as that moves out across the landscape, you can see how different features might be more preferential to species movement. And again, this is just an overlay with an OS map, and you can really see how the landscape features play an important role to horseshoe ecology and the movement of the species across the landscape. And I just want to highlight one of the sections here, and I'll zoom in a minute. This road here, you can see that there's a drop in current or activity within that area. And if we zoom in on it here, the colors in this map are actually switched around. And you'll see here the red is high energy or high movement or high predictability of species movement. The black triangles are street light placements. So you can see here how street lights can really have an impact in terms of negatively influence how horseshoes might move in the landscape. However, one of the good things about using a software like this is that it's quite a visual tool. So if we want to go to planners or policymakers, it's quite a visual tool for them and quite easy to understand. And it may not be the case, for example, in this instance, that we need to turn off every single street light along the road to help bat species move across the landscape. We could be looking at putting in specific measures, conservation measures like cowling lights or turning off a single street light rather than doing it all. So a lot of when we have these discussions, a lot of around it is public safety. So this will allow us kind of, rather than just to switch off the entire street, is target these areas to allow better species conservation as well. And again, this map, the colors are switched around again, apologies. The blue is high kind of energy. What I'll say is this, I'm going to just look at two examples here, and this yellow box here is looking at you can see there's a gap here. So this is just these areas, sorry, these boxes here in the center of it are houses. It's quite a dense urban area, and there's a road running north-south and east-west through this village essentially. And where the yellow box is at the top is where we thought bats might, based on the model, where bats might cross the road to access foraging grounds on the eastern side. So what we did was, to test this, we placed bat detectors north and south of this location and at this location. And lo and behold, the model was correct. And the highest greater horseshoe bat activity occurred along sort of where this pinch point is in the yellow box. So it really helps us identify where species might be crossing roads. And again, you know, if we're looking at species conservation and practical measures, we could be looking at turning off a single street light here to really allow access for species to move across the landscape. One of the other areas or interesting things that came out of using this sort of modeling technique is identifying areas that we would have perceived as not being suitable for species movement. So this second box here, you can see there's a bit of blue coming through the landscape there and through the center of the village. And again, this is lots of houses, lots of street lights. But because we got this kind of little flow of energy, we wanted to test this, and we placed bat detectors along that sort of corridor within the yellow box, and then either side of it, east and west of it, to kind of test this presumption. And again, we had greater horseshoe bats flying through the center of the village along these sort of corridors. And when we went to check it, you can kind of see why although it's still kind of highly urbanized, there are some mature tree lines there which really allow the species to move across. So this really helps us, again, come back to practical conservation measures. If we want to target these areas and increase species movement across these areas to ensure permeability to foraging areas or potential foraging areas to the south of it. So it's really useful. And one more interesting thing is, when I was going back and talking about the influence of the centre of agricultural fields, or testing every different type of linear feature within the landscape, and not just to go to those ones that we perceive to be important. This there's a managed hedgerow, I suppose, in the middle of this picture. You have an arable field in the foreground, and then kind of in the background, and then behind that is a lovely woodland with, you know, a 5 to 10 meter pristine river and lovely tree line behind it or within it. And the model was picking up really high activity or potential activity or high movement of species along this one managed hedgerow. And so we were doubting the model's performance. So what we did was, again, we put out bat detectors at these locations, and we put it in the managed hedgerow there. We put it in the river in the middle of the woodland and along the woodland edge between them. And lo and behold, we picked up the highest amount of greater horseshoe bat activity in comparison to any other bat detector at a similar distance to the roost at this location. So this one managed hedgerow was extremely important to the movement of the greater horseshoe bat at the landscape scale, despite only across the other side of the field there being, you know, a nice woodland edge with much better, you know, tree line to it. And then when we look at the context of this managed hedgerow in relation at the landscape scale, we see that leading up to this managed hedgerow and after this managed hedgerow, so I suppose if you look at it from the right hand side leading up to it and the left hand side away from the hedgerow, there was good habitat. There was really good foraging habitat further, I suppose, right in this picture, where the bats are obviously trying to get to. So this is why it's really important to look at a landscape scale element of species movement, and not only look at areas where we might perceive to be important. So, you know, if you're looking at development within this area, you might only put a bat detector along the tree line edge behind it. You might do your transect across the unmanaged or the managed hedgerow, but unless you have a static detector overnight or over the course of the week, you may not pick that sort of activity up. So it's really important to look at a landscape scale when trying to make these assessments. And then this is just kind of, we were working how these sorts of models might influence policy or planning. So we were working with Devon County Council as such, the local authority in Devon, and they were looking at their future planning for urbanisation, housing developments. As we're all fully aware, you know, there's a huge housing problem in Ireland and elsewhere in the world. And in one sense, we need to build houses, but we can also do this strategically and identify corridors for species, not only bats, but for other species to move within the landscape. And so we don't cause fragmentation, have the least impact on the species, and allow genetic flow at a landscape scale. So we were trying to help them identify areas, you know, they were mapping areas where they had already zoned for urban or houses, and then those areas where they wanted to kind of build in the future, potentially build in the future. So we were looking at what we're kind of calling flyways across the landscape, and how our model could influence planning departments at you know, a local authority, or again, you know, at a national level. So these are kind of one element which kind of feels is really important. Sorry. So that's kind of the element of what I looked at in terms of my PhD and postdocs and stuff like that. So we also then translated or transposed this kind of information. I did the work I did on greater horseshoe bats back to Ireland at a national level. So this is the 6 west counties of Ireland where we have lesser horseshoe bats. And we looked at all the lesser horseshoe roost locations and looked at the resistance values at a national level, and tried to identify corridors between every single roost across Ireland. And as you can see here, I know that there's genetic studies to also back this up, but we can really see here the fragmentation at a national level between, I suppose, three areas: your very north, your central roost locations, and your south roost locations. So this really highlights how, at a national level, there's an impact for fragmentation. We also, working with Tom O'Donnell and Cork County Council, we were looking, I don't have any names on this, apologies. This is around Blarney and Cork. We use Circuitscape to map functional connectivity within the landscape between roost locations. And again, kind of similar to what I've talked about previously, trying to identify those landscape features, hedgerows or rivers that might really influence species movement, trying to identify those corridors within urban areas, and how can we best plan strategically for both requirements in terms of biodiversity and any other national requirement. This is really important. And again, it's another element with working with Vincent Wildlife Trust up in Galway, similar to what the approach I took in Devon. We're looking at more fine, higher resolution information around sites in Fidon in Galway, and how lesser horseshoe bats might use the landscape. And what's really interesting in this case is that whilst we had, say, 3 linear feature types in England and Devon, we had unmanaged, managed hedgerows, tree lines. What we also had to include in this one was stone walls, because stone walls within the Irish environment, across western side of the Irish environment, it's actually a key feature for species as well. So it's really interesting. And I suppose, just kind of to wrap up, and talk, the importance of these types of tools is that, as said before, they're a great visual tool for planning. So if we're talking to councils or landowners, developments, I think having a physical image of an area is much easier to understand, rather than just saying, this is important. At least here they can visualize, see how important it is in comparison to potentially other areas in the landscape. The models will allow us to identify pinch points in the landscape. Where can we target those practical conservation measures, have the highest value for our money, prioritize the conservation areas. If we have limited money or resources, where can we monitor? Where can we put in new hedgerows? Anything like that, where we might have limited resources. These sorts of models can really help us identify those areas. And we're all stuck for a bit of cash at a national level, so it can really help us. And they also have great predictive application and value. So what I mean by this is that we, for example, if we have a new road going in, or a new development, or we want to put in street lights, we can put all that information into the models and then assess kind of how that might influence the species movement at a landscape scale. Or likewise, if we're wondering which street light to turn off or which measure to put in where, we can assess that before we actually undertake the measure, to see how we can get the most value out of what we're doing. So that, I'm going to leave it there, and hopefully time for some questions.